Hello everyone, it's Professor Beamer. In this video we're going to be working through section 1.11 on formulas and literal equations. Hopefully you've had a chance to practice some of those skills in section 1.10 on solving equations, because we're basically going to be doing the exact same thing, except more variables involved. Because again, this is sort of really probably one of the most important sections in this entire course, because when we're using math, one of the most common ways that we use math is in the use of formulas. What's a formula? Sometimes called a literal equation. A formula is an equation that expresses the relationship between two or more related quantities. Again, you can see these in industrial examples and medical examples and everything. We have some quantity being related to some other quantity. Chances are everyone in here will at some point see Ohm's law, which is an expression that relates voltage, current, and resistance all to one another. So if we describe voltage by the letter V, current by the letter I, and resistance with the letter R, we can describe it in this one equation. In fact, some instances, some contexts, you might see voltage described with the letter E, but it's the same idea. So when we have this one relationship, one great thing that we can do with this equation is we can basically think about it as if I have two pieces of these information, I can figure out what the other one has to be. So if I have current and I have resistance, I just multiply them together to get voltage. We looked at a similar example in a previous section, but we hadn't described it with this nice formula. And the other thing we can do with this formula is we can isolate it for another variable. So if I know that the voltage equals the current times the resistance, I can take this equation and solve it for current. How do we do that? Well, we apply the same idea that we used in the previous section. In order to isolate the variable I, I'll need to divide both sides by R. I need to undo the multiplication by R that's happening. So if I divide both sides by R, then I will get that the current is equal to the voltage divided by the resistance. Finally, I can also take this equation and solve it for the resistance. So if I take this equation and solve it for the resistance, well, I want to do basically the opposite that I just did here. I want to divide by the current I to isolate that variable R. Again, if I divide both sides by I, then that goes away on the right side, and then here we'll have V over I. Note also, like we did in the last section, we prefer to have that isolated variable written on the left side, so that's sort of the convention that we have. So the resistance can be found by dividing the voltage by the current. Now you could think about this as three separate rules, but really, writing it as this equation, we can see that it's really all the same relationship. If I know any two of these pieces of information, I can get the other one using this format. So a lot of you will probably also be taking physics at some point, and in physics, one of the things we talk about a whole lot is we talk about the motion of bodies. So for instance, if we have some object that has a constant acceleration, like the acceleration due to gravity, and if it has some velocity v given at time t, and some v naught, which is the initial velocity, then there's an equation that relates these things. It actually comes from calculus, that v is equal to the initial velocity plus the acceleration times the time. Now, one thing we might want to do is, given all this information, we might have three pieces of information here and want to find the fourth, right? We have four different variables going on here. So let's say we knew the velocity at some time t, we knew the initial velocity, and we knew the acceleration. How could we get time in terms of those things? Well, this becomes a sort of equation like we saw back in the previous one. The only thing that's different is that instead of having numbers here, we have variables, but the process is identical. We want to isolate the variable t. Well, in order to do so, we have to undo the things that are being done to it. Well, I've got this number plus a times t. The first thing I'll need to do would be subtract away that quantity that's being added here. So if I subtract that, I'll get that v minus v naught, or v sub 0, and then that's going to be equal to the product of a and t. Well, now we're almost home free. We want to get t by itself. Again, we have currently a times t. We want to undo the thing that's currently happening to t, which is to say divide both sides by a. So what does that say? Well, again, I'm going to write my isolated variable on the left-hand side. That isolated variable t equals to this expression, v minus v naught all over a. Again, you can think about this as a different equation, but it's really not. It's just a different expression of the same relationship, where you sort of highlighted one variable in terms of the other ones. Speaking of gravity and acceleration, there's another physics principle which is called Newton's law of gravitation. I won't get into what all these variables represent, but it has to do with how the force between two large orbital bodies, basically, or really to any sort of bodies. We'll use it to talk about things like orbits and such. So that equation is given by F is equal to g times little m times big M, all divided by r squared. And what I want us to do is solve the equation for that variable little m. So again, at this point, we just kind of imagine, you might think about, well, what if all these things were just numbers, right? N is going to be multiplied by some number g, it is in fact a constant, and then some other number m, and then we're dividing by r squared. So that means I need to undo all of the stuff that's happening to m. Well, we talked about how, with that order of operations thing, that multiplication and division basically happen at the same time, so we can sort of undo this in kind of whatever order we feel like. What I would suggest that we do is get rid of that fraction, right? Sometimes fractions just make things a little bit harder to work with. So if I want to isolate that variable little m, I can multiply both sides by the denominator here. So if I multiply both sides by r squared, the left-hand side of this equation would be f times r squared. And the right-hand side, well, if I multiply by that denominator, like we saw in the previous section, if you multiply that expression by r squared, those two will just divide out, and we will simply have g times little m times big M. So that's kind of nice. It's a sort of nice general guideline. When you have a fraction, sometimes it's kind of nice to get rid of it, and the way you can get rid of that is by multiplying both sides by that denominator. Well, now we want to isolate for this variable little m. Well, again, we need to undo the things that are currently happening to it. We're multiplying it by g, and we're also multiplying it by big M. So let's go ahead and divide both sides by g and m, big M. I wasn't the one who chose these letters. This is how they're expressed in physics. You can blame the physicists. So at this point, if we divide both sides by g and m, there's nothing left other than the variable that we wanted to isolate here. And what is it equal to? Well, again, these things all cancel one another out. And we'll get f times r squared over g times m. I mentioned this in the last section, but I'll reiterate it. The formulas that we are dealing with when we come to talking about applications, they're not something that we need to memorize for the purposes of this course, but chances are you will get to a point at some future course where you do have to have all these formulas that you memorize. In terms of what formulas you really need to memorize for this course, we'll get into some of that a little bit later on. Really, we're more interested in using them and being able to have this sort of skill rather than this memorization. Generally speaking, you can usually just look stuff up. All right. let's explore some more ideas, and let's deal with some concrete numbers here. And again, one of the things, the reasons why it's helpful to be able to solve an equation is because it makes it easier to find some particular unknown value when the other variables are known. So one particular equation here is an equation that relates degrees Celsius with degrees Fahrenheit. In a lot of medical applications, we tend to think in Celsius just because the metric system is more dominant in a lot of scientific disciplines, but for various historical reasons, we tend to think about temperatures in Fahrenheit on a sort of colloquial level until the metric system becomes more popular. So body heat, at least as it was recorded like 150 years ago, is 98.6 degrees Fahrenheit. This is a sort of well-known number. Might actually be a little bit lower than this, but I'll let you explore that on your own. But what we want to do is go ahead and find this temperature expressed in degrees Celsius. So what we're going to do here is what's called evaluating this thing. So I'm going to go ahead and throw that word in there just because we haven't seen it yet. So we are going to evaluate this formula, and evaluating formula simply means what you might call plugging in, replacing the appropriate variable with the number, and then simplifying that expression. So we're going to go ahead and replace that variable f with this number 98.6. So here, this is going to be 5/9 times 98.6. Let me write down the right number. There we go. Minus 32. Now, we can evaluate this way, however which way we want to. If we're good about using parentheses, I can actually just type this right into my calculator as it says. Do 5 divided by 9 times 98.6 minus 32. See what it works out to be. It works out to be 37. So this is 37. And we're going to include units. Anytime we have units, we're going to make sure that we include them. So this would be in degrees Celsius. Now, this equation, the way that it's expressed, is super useful for being able to figure out the temperature in Celsius given the temperature in Fahrenheit. But if we want to go in the opposite direction, it would be more useful if we had this equation in terms of f, which is to say if we had f equals some expression involving c. So that's what we're going to do here. Again, very similar to what we did in section 1.10, we want to isolate the variable by undoing the things being done to it. Well, here, we've got this little fraction here, so we have to think, what's actually going on with the 5/9? There's really two things that are happening, right? You're multiplying the expression by 5, and you are dividing it by 9. So if I want to undo those two things, I'm going to have to divide by the 5 and multiply by the 9. So let me go ahead and do that in the first step. I could do this in two separate steps, but since multiplication happens at the same time as division, we can just do them in one step. So I multiply it by 9 to undo the division by 9, and I divide it by 5 to undo the multiplication by 5, just to sort of show you what's happening here, breaking it down into as much detail as we can. I'm multiplying both sides of the equation by 9 and dividing by 5, or you can think about that as multiplying both sides by 9/5, which is what we call the reciprocal. We used that word in a previous section. The reciprocal of 5/9 is 9/5. Why do we care about that? Well, remember that when it comes to fractions, we multiply across, so we get like 45 over 45, or the other way we could observe it, we've got a 9 common to the top and the bottom, we've got a 5 common to the top and the bottom, so that expression would completely cancel out all of those fractions that we have going on. Well, that means all I would have left now would be the f minus the 32. No need for parentheses because nothing else is happening there. And to get f by itself, we go ahead and add 32 to both sides. I'm going to go ahead and switch around the order of these things so that my isolated variable is on the left. Again, that's just sort of a notation default that we like to do. So we've gotten rid of everything that's on that side of the equation that has f on it. And what's left on the other side, well, would be 9/5 times c plus 32. So now that we have this equation, we could go ahead and figure out, okay, what would be a particular temperature at some room temperature. So if we say that room temperature is 20 degrees Celsius, there's actually some slightly different conventions on this, but if we say that room temperature is 20 degrees Celsius, let's figure out what that's going to be in Fahrenheit. Well, this equation is much easier to use than this one, because if you used this one, you'd have to plug in 20 for c, and that would basically become a problem like we did in the previous section, isolate for f. But the advantage of having done so with our formula is I've already done that work. I can go ahead and just use this one formula and replace that variable c with the number 20. So what do we get when we do this again? 9/5 times 20 plus, oops, let me make sure I plug in the right number in my calculator, plus 32 gets us 68 degrees Fahrenheit. So you'll see in a lot of like chemistry manuals, there's certain assumptions about like how things interact with one another, and they usually specify that this is what happens at this fixed temperature of 20 degrees Celsius. In a completely different direction, we could look at this formula here, a equals p times 1 plus r to the power t. So we can actually have a variable be an exponent. This is actually a formula from finance that relates the future value a of some deposit of p dollars in some account that earns an annual interest rate r expressed as decimal after some number of t years. There's so much that we can say about this. Again, not a formula that we have to memorize, but it's a useful thing to know in terms of how it affects your personal finance and why it's important to save for retirement and such. So if we want to solve this formula for p, well, let's think about what's happening to p here. P is being multiplied by this expression at 1 plus r to the power t. So if we want to undo that multiplication here, again, we just need to divide. But what we need to do is divide by that entire quantity. So if we divide by that entire quantity, the 1 plus r to the t, we will get here that p is equal to a divided by that whole thing, 1 plus r, all being taken to the t power. If we've solved this formula for p, what that means is if I have the other three pieces of information, I can figure out what p would need to be. In fact, let's go ahead and do that. Let's answer this question: how much would you have to deposit today in order to have $10,000 saved up in 4 years at an interest rate of 6%, which would be in decimal form 0.06. Remember, percent literally means divide by 100. If you divide 6 by 100, you have 600ths, or 0.06. And we're going to round our answer to the nearest dollar. So one of the things when we're actually evaluating a formula in a context like this, we need to go ahead and identify what each of these variables or what each of these values corresponds to in terms of which variable it is. So let's see, 4 years, that's clearly saying that t is equal to 4. The interest rate is 6%, which is to say r is 0.06. And now the last tricky part is what this number is going to correspond to. Well, if we want to have $10,000 saved up in 4 years, that's the amount in the future, not the amount we would need to invest right now. So that tells me the amount I need to have in the future is that $10,000. So those are each of the pieces of information that I need. Now all I need to do is evaluate my formula here. So p will be equal to that number, 10,000, divided by 1 plus 0.06, all to the 4th power. there's a bunch of calculator steps that are going to get involved in this thing. Let me show you a couple of different ways. One way would be to sort of break up your intermediate steps and really think about it like a PEMDAS order of operations sort of thing, right? So in this expression, the very first thing we need to do is work within the parentheses. Take 1 plus 0.06, which is 1.06, of course. And now we're going to take this expression and take it to the fourth power. We mentioned the answer key in a previous one, or you can simply use the operation here and it'll automatically default to doing that answer. So I could press the exponent button. I want to take that thing to the fourth power. Now, exponents are kind of funky because oftentimes you get weird answers out of them, but that's saying that this denominator is equal to this about like 1.262, et cetera, et cetera, et cetera. So the number I'm dealing with here is like 10,000 over. Again, it's about 1.26247, et cetera. Now, if we were to lop off any of the digits in this expression here, our number might be off, and that might be a number that's off by dollars or tens of dollars or hundreds of dollars. So instead of doing that, we want to use this exact number as it's stored in the calculator. So again, we're going to utilize this answer key, but we're going to have to observe here that that answer from the previous step is actually the thing I want to divide 10,000 by. So I can write this as 10,000 divided by the thing that I just got at the previous step. So we can press second answer. Again, your calculator might have these things in a slightly different spot, but generally speaking, they all have an answer key. So if we divide 10,000 by that answer, we get this number here. And the nearest dollar here means the nearest whole number. So that would be $7,291. Now, the other way to set up this problem here would be to just do it all in your calculator. But if we're going to do it all in our calculator, we need to make sure that we're careful about exponents and parentheses and all of that stuff, right? We need to enter in the correct number. So we want to take 10,000 and divide by the quantity 1 plus 0.06 taken to the fourth power. So I'm going to put in an extra parentheses just to be careful. I'm going to take 1 plus 0.06 to the fourth power and then divide by that. I think it's a redundant parenthesis. I didn't need to have it there, but that's just to make sure that I haven't parsed it incorrectly. We get the same value that we just got. So again, whichever you feel more comfortable with, you might want to take some intermediate steps, or if you just want to crunch it all, that's fine as well. The last thing we can do is just check this thing. Does it make sense, right? The way that saving money works, if you're earning interest on it, it means that you will have more money in the future than how you started with. Again, there's a lot more that we could say about that, but I will save that for another math course if you're curious. But it seems vaguely reasonable that if we saved up something like around $8,000, that in a few years we'd have slightly more than that. Again, not a formula that you need to memorize, but it's like a super, super important formula for understanding how life works. All right. Let's do a couple more of these solving equation things. Again, it's very similar to what we did in section 1.10, but we have to think about it a little bit more algebraically. One of the reasons why we're exploring all these formulas is because we're going to see them again in chapter 2, because in geometry, there's a whole lot of formulas that describe ideas like, for instance, area. So one of the things we'll talk about is the area of a trapezoid that has a height h, bases b1, b2. If you don't understand what all these things mean right now, don't worry, not that big of a deal. But what we want to do is take this equation and isolate it for that variable h. Well, this is going to be kind of similar to the Fahrenheit-Celsius problem that we did a moment ago. If we want to isolate this thing for h, we have to undo the stuff that's being done to it. We talked about how sometimes we might want to multiply out, distribute things, and sometimes it's actually nice to not distribute. In fact, I'm going to choose to not distribute here because if we think about what's happening to h, there's basically two things. It's being multiplied by a half, and it's being multiplied by this b1 plus b2. So if we want to undo both of these operations, well, to undo multiplying by a half, since that's the same thing as dividing by 2, you could multiply both sides by 2. So the left-hand side of the equation would be 2 times a, and then the right-hand side of the equation would be h times b1 plus b2. Again, if I double both sides of the equation, doubling it will remove the 1/2 that's right there. Now, in order to isolate this expression for h, currently h is being multiplied by this quantity, b1 plus b2. So just like we did on the previous problem, we could divide both sides by that entire quantity, that b1 plus b2. If we do so, well, we'll have 2a divided by that whole thing, b1 plus b2. And that's really it. That's as far as we can go. There's no rule for simplifying this expression beyond that. We will just sort of leave it the way that it is. The advantage of doing so is it makes it easier to answer a question like the following. Let's say we wanted to figure out how high do we need to make this trapezoid to have a particular area. So if we want the area to be 42 square meters and b1 and b2 have the values as shown there. Well, all we need to do is plug in these numbers in here. We get 2 times 42 over 5.3 plus 7.4. We can probably just plug this all into the calculator, just noting that the denominator is that whole expression. So when we're evaluating this in our calculator, we probably want to go ahead and put in parentheses just to indicate that both of those numbers are actually in the denominator. If we forget the parentheses, we end up doing something different than what we were actually trying to do. So here we got 2 times 42, and then divided by the sum of 5.3 and 7.4. Voila, we get something like 6.6. So now, again, we're going to use our default principle that we are going to express these values as approximate, right? If we're actually measuring these things, all of these we're taking to be approximate numbers. Note that every single number here has 2 significant digits, so we're definitely going to look for 2 significant digits here in our answer. So we're going to report this thing as being 6.6. And it makes sense that if the units I'm talking about are meters squared and meters, that this would be given in terms of meters. We can explore that a little bit further, but I'll wait till chapter 2 to kind of get into a little bit more of working with units. 2 other equations that I want to introduce here. One, and just another one involving a bunch of various variables that comes up with dealing with magnetic fields, something that happens in electronics a lot, in physics as well. So we've got here b is equal to, this is a little Greek letter, it's called mu, so mu sub 0 times I over 2 pi r. Remember, pi is a number, it lives in your calculator, among other places, but we'll explore this a whole lot in the next chapter, but it's equal to about 3.14, etc. But we're actually going to leave it, basically just treat it as a variable, essentially, and just kind of multiply or divide or whatever both sides by that expression. So let's say we actually wanted to solve for the variable that was down here, this variable r. One of the things we discussed before was that we can essentially get rid of a denominator by multiplying both sides of the equation by that denominator, and that will make it so there's not a fraction anymore. So that's what we'll do here, is multiply both sides of the equation by that expression, 2 pi r. If we do so, we will get 2 pi r times b on the left-hand side, and then on the right-hand side, well, if I multiply this thing by the denominator, that expression just goes away. We get mu naught times I. Mu looks kind of like a U with this little extra sort of tail at the front. Well, having done that, we have a much simpler equation to deal with. It is now much easier to see how we solve this thing for r. We just need to undo the multiplication that's currently being done. So we need to undo multiplication by b, by 2, and by pi. We can actually just do that all in a single step by dividing by 2 pi b. If we do so, everything on the left-hand side of the equation has canceled itself out, except for r, the variable that we wanted. And what is r equal to? It equals to mu sub 0 times I over 2 pi b. One last example that I want to visit here is to talk about a circuit with parallel resistors. Again, if you're dealing with electronics and physics, chances are at some point you'll talk about circuits and what it means for resistors to be in parallel versus in series, but there's an equation that relates the total resistance with the individual resistance of those resistors. So let's say that you have some desired total resistance that you want to get out of the circuit, and you have that one of the resistors is going to be 330 ohms. You want to figure out how much do we need to make that other resistance R2. I can get really fancy here and solve this equation for R2 in general, but that's a little bit more complicated than I want to deal with. Let's say I just want to answer this particular question. Well, what we can do is we can actually evaluate this formula at those two values and then go ahead and isolate R2. Let's see what's going to happen when we do that. So the total resistance is 180, so we want that left-hand side to be equal to 180. And then on this right-hand side, we know that R1 is 330, but we don't know R2. Whenever we don't know R2, or whenever we don't know a variable, we just leave it as that variable and then see what we need to do to get it by itself. In the denominator here, we've got 330 plus R2. Well, here, this one's even a little bit trickier than the previous ones that we've seen because we got the variable showing up in two separate spots. And it might be tempting to try to think about like canceling things, but unfortunately we can't do that. We can only divide out stuff when the factors are in what we call factored form, when it's like all just multiplied out. So unfortunately, there's nothing we can do in terms of canceling or simplifying things out, at least not without messing everything up and getting the wrong answer. So instead, we're going to use a sort of similar principle as we did before. When I have these variables here, when I've got a variable in the bottom of this equation, I can get rid of a fraction by simply multiplying both sides by that denominator. So let's go ahead and show that. We're going to multiply both sides by the denominator. And again, this that whole quantity, 330 plus R2. So let's go ahead and put it in parentheses to illustrate that we want to multiply by that whole thing. So we multiply that whole thing by the 330 plus R2, and that will be equal to just the numerator. Again, we multiply both sides by the denominator so that it would cancel out on the right-hand side, and the left-hand side is just 180 times that whole denominator. So we actually saw some equations like this in the previous section. Now we actually have context when it would actually be meaningful for this. So we need to go ahead and isolate that variable R2. Well, as we discussed in this previous section, we can distribute across parentheses first, get my like terms on one side, do what I need to isolate the variable. So if we go ahead and distribute here, 180 times 330 equals to 59,400, okay? And then 180 times R2, well, again, we don't know what R2 is, but the best that we could say is simply whatever it is, we're multiplying it by 180. And that is going to equal to 330 times R2 on the right side. Now we want to get the like terms on one side. So we want to subtract away some of the terms from either side. I think it makes more sense to subtract the 180 R2 from both sides, because then I'll just have a number on the left-hand side. And, oops, I need that equal sign there. And then I'll just have some fraction, or some number of R2s here on the right-hand side. Again, having subtracted that 180 R2, the only thing that's left on that left side of the equation is 59,400. And here we're doing that combining like terms thing. Both of them are some multiple of R2, so we can just look at the numbers in front of it and simplify that part. 330 minus 180 works out to be 150. So we get 150 R2. Almost done. Last thing that we need to do is to go ahead and to isolate the expression for R2. The way that we do that would be to divide both sides by that number that's currently being multiplied by R2. Excuse me. So we go ahead and divide that expression by 150 here. Well, here's where we'll get out our handy-dandy calculator. 59,400 divided by 150 works out to be 396. But before we finish that problem out, let's revisit this idea of significant digits, right? In my problem here, both of those numbers have two significant digits, so the answer that I'm going to look for also should be phrased in terms of two significant digits. So let's go ahead and write that here for our answer, that our resistance is going to be 400. Now the very last thing that I'm going to do is give this thing a unit, right? Both of these things are given in terms of ohms, so this thing is also given in terms of ohms. So that's the thing that we would need to put into our circuit in order to get that total desired resistance of 180. Weirdly enough, when we have those two resistors, the total resistance in parallel actually ends up being less. I will save that for an electronics or physics course for you to explore more of why exactly that's the case. One last comment on this. In practice, you wouldn't even really think about this in terms of significant digits. You think about, okay, what are the resistors that I have, and which of them actually are the closest to this number that'll do the job, in essence.